Okay, in that case, I'll get started here. So I'm going to talk today about deep learning and what opportunities as well as threats that it might mean for us in medical imaging. You can see my title there. Oh, no video? According to this, I'm sharing microphone and screen. Okay. So some people are seeing video and others aren't. If let's see, if people still are not seeing video, so some people are seeing it and some aren't. Okay. Oh, okay. So according to this, I'm sharing my webcam, but you know what? I'm not that good looking anyway. So let's just proceed with slides. Okay. So we will go this way. Disclosures, I'm involved with a couple of companies. None are directly related to that. I do get some support from NVIDIA. I'm also involved with the American Board of Imaging Informatics, which if you know what CIIP is, and I'm also on the RSNA Informatics Committee. All right. So you may or may not have seen this report out of Oxford University that figures that 47% of US jobs could be automated within the next 2 decades. My guess is that's probably equally true for Europe and the rest of the world, perhaps even more challenging for some of the lesser developed part of the countries. And if you look at that list, number 5 on there is medical doctors. Now, at least the Obama White House or report out of the US is that there's an 83% chance that workers earning less than $20 an hour will be replaced in 5 years. So it does seem like there's probably more challenge to some of the lesser paid people. But I think ultimately the major point of this is that people who do a very stereotypical type of job are probably at greatest risk for replacement. For those of you who are in the deep learning community, you almost certainly know who Andrew Ng is. And Andrew Ng told The Economist that a highly trained and specialized radiologist may now be in greater danger of being replaced by a machine than his own executive assistants. And the difference, again, is because she does so many different things, his perception is that we sit in a chair and convert images into reports. And of course, if that is how we view ourselves, he may well be more right than we think. Ezekiel Emanuel, who used to be in the Obama White House, also exuded this opinion both in the New England Journal and at a American College of Radiology meeting, where he suggested that radiologists could be replaced by computers in the next 4 to 5 years. So clearly, there's a sensation among us radiologists that we have this target on our back and that computers are out to replace us. So that's, I think, what's generating a lot of angst in our field. So what I want you to do is remember 3, 2, 1, and you'll have better understanding of what I mean by that by the end of this talk, okay? But just think 3, 2, 1. So now I'm going to give a little bit of background information and talk about what is machine learning. And the machine learning is a part of artificial intelligence. It it goes out and it finds patterns in data, and I'm getting a message there. Does that help? I can't see text anymore, so hopefully that will be fine. Machine learning finds patterns in data. These patterns can reflect properties of examples, and that's known as supervised machine learning, or it can provide identities of clusters or patterns that are groups of examples. That's interesting, it's moving on its own. Sorry about that. I'm not sure what happened. And this type of machine learning is known as unsupervised, so it's sometimes called clustering because it identifies clusters within otherwise unorganized data. And there are other types of artificial intelligence, things like rule systems. For those of you who are history buffs, really the start of machine learning was the artificial neural network. And the challenge with artificial neural networks is that although they were based on models of the brain, they quite frankly didn't work very well. And so over the past couple of decades, other machine learning methods have become much more popular. Naive Bayes technically maybe isn't a machine learning method, but it uses statistical predictions to identify ways of finding patterns and whether an example is one example, whether one example is a certain class or not. Support vector machines are probably the most heavily used in CAD products today. Essentially, these try to find a way to remap data into some other sort of space and then to separate the two classes that you want to separate. And then the more recent technology is called a random forest classifier. And this essentially is where you have a decision tree. So for instance, you can imagine if you start with a lab value and you say if it's greater than a certain number, go to the right side, otherwise go left. And then the next level down, if you took the left branch, you look at a different lab value and you say, well, if it's less than this, turn to the left, otherwise go right. And so that's how it gets its name for being a tree. And if you then have multiple samplings of the data, each producing its own tree, you then combine all the trees together, and that's why it's called a forest. And because you are doing a random sampling, that's why it's a random forest. And so you then get a better statistical representation by having many samplings. And the beauty of a random forest classifier is that you can get an understanding of how the machine made its decision. That can be much harder to understand from a support vector machine. So artificial neural networks are a key technology in deep learning. So I'm going to spend just a little bit of time explaining how they work. So if you have an input layer, you, for instance, could take the pixels of an image, say the T1 pre, post, and flare image, and maybe they have values of 45, 322, and 128 for each of the 3 different types of pulse sequences at that XYZ location. And then the reason that we have these lines here is that we then take the value here and multiply it by some weight and then put that into the next layer. And you do that for each of these nodes. There are all these different weights. And so then this layer here would take these weights that are the multiplied weights that are fed to it, and it would then apply some activation function where it says, okay, if the value is greater than 100, I'm going to have 1 as the output. If it's less than 100, I might have 0. Rarely do they actually do simple thresholding like that, and I'll talk more about activation functions later. Then from that layer, they again apply a number of weights and ultimately try to get some decision, for instance, like 1 or 0, whether it's tumor or normal brain. The way that artificial neural networks learn is that it looks at the output node value computation, that 1 or 0 at the end, and it looks at for all the pixels in an image, and you would have to say, well, this part of the image is tumor and this part of the image is not tumor, and it looks at all the population of pixels and it decides how many of those it got right and how many it got wrong and computes some sort of an error. And the error, of course, basically is the expected output versus the computed output. Rarely do you get it to where the error is 0, but oftentimes the error can get very close to 0. What you do is you take the error then and you try to figure out a way to update the weights in the network in order to improve the error so that it becomes a smaller value. So you take the old weights times this error times some sort of a learning rate. And typically the learning rate is high at the beginning, and then as the error becomes smaller and smaller, the learning rate also becomes smaller so that you essentially settle in on the optimal set of weights. Okay, so that's the old style machine learning. Why is there all this hype now? And really, this is the key point here. In the year 2012, there was a huge jump in the performance in one standard evaluation of machine learning known as the ImageNet Challenge. So the ImageNet Challenge is a collection of thousands and thousands of images with things like cats and dogs and flowers and whatnot. And the challenge was to see how many of those pictures it would get right. And up to 2012, an increment of less than 1% was considered an important change. But suddenly in 2012, there was suddenly a change of like 15% improvement of how well the algorithm could perform. And this was a deep learning algorithm compared to the old ones being a traditional machine learning. And over the ensuing years, these are all now deep learning methods that are resulting in substantial improvements on this ImageNet challenge. What's also interesting is that actually one of the people who does deep networks tried to actually do this challenge himself. And it wasn't like he just looked at it and decided it was a cat or a dog. The challenge is actually much more complex than that. It is to identify the species of flower or the breed of dog or something. And he said, well, you know, if my computers get 100 hours of training, I'm going to take 100 hours. So that's why it's human and not humans. He tried to get some of his colleagues to do it, but they weren't willing to put 100 hours into training. But he spent 100 hours learning from the photos, and you can see that his performance is at 95%, and in 2015, a computer eclipsed him. So this is why there's so much excitement and expectation that computers are going to replace humans, including radiologists, in recognizing what's going on in an image. So what is deep learning? Well, it's called deep learning because it uses many layers. As I said before, artificial neural networks were the starting point, but they typically had 3 or fewer layers just because the computations for doing more was just too complex. In fact, a deep learning network, one example being a convolutional neural network, or CNN, will have many, many, many layers, like 50 to 100 layers. And actually, each of these boxes here actually represents multiple layers. And there are also multiple types of layers. So the initial part is convolutions, which some of you may be familiar with. It's essentially a filtering function. And then a pooling function says, out of that convolution, I'm going to take, for instance, the maximum value. That's called a max pool, and that's fairly commonly used. And then there might be another layer of convolution, and then maybe another layer of pooling, and more convolution, more pooling. And actually, there are activation layers and whatnot that are also sitting in here that I haven't shown. And then at the very end, you might have a fully connected network, which is like that artificial neural network that I showed you before. Okay, so now with that as background, why is deep learning happening now? And really there are 3 reasons, okay? So I'll give you, there's that 3 that I wanted you to think about. We all know that computers are getting a lot more powerful, and so that's clearly one driver. But also there are many important theoretical advances, and without these, the power, quite frankly, wouldn't matter. And then finally, there's substantial investment. I'm going to go into each of these a little bit more detail, and I'm actually going to start with the theory because I think this often gets overlooked. There are a lot of important theoretical advances that have really made deep learning possible. One place where an awful lot of the deep learning papers are at this website. So if you really want to learn about deep learning and what's happening now, this is the website to go to. Okay, so what are some of the important things? Convolutional layers. Actually, this isn't all that new, but the computation power to run them and make them practical and therefore to include in a neural network is relatively new. And of course, this is really appropriate for images. For other types of tasks, convolutional neural networks are really not the right tool. Pooling. It would seem like you would want to have the precise value, but in fact, it turns out that things like simply taking the maximum value often can find the feature that that convolutional filter is identifying. And so max pooling seems like a simplistic idea, but it actually turns out to be powerful. Regularization. So this is how you figure out what the appropriate weights are and what the activation function is. So again, the artificial neural networks were based on human physiology like neurons, but it turns out that a much simpler function like a rectified linear unit, which essentially says any value less than 0 has 0 as the output, and anything greater than 0, you just pass on that value. Turns out to be a much more effective activation function. It's also a lot easier to compute. Now actually people are starting to play with what's called a leaky ReLU, which means if it's negative, you actually do give some value. So it's essentially two linear components that changes its slope at the 0 point. Residual neural networks are relatively recent, and these seem to be very powerful. Essentially, this forces each layer to learn, and so it's really not, it's really a layer, it's not a network per se. But this really has made the deep networks much more effective, because otherwise the challenge is you didn't know where to apply that error function, which layer of the network to update the weights for. Another new thing is what's called cascaded architectures, and essentially it's almost like putting one complete deep neural network. It's if one is good, how about two? And again, I'd encourage you to go to this website because there is something new in this space every day. Exponential compute power. Okay, you'd have to live under a rock to not know about something like Moore's Law, right? And so Moore's Law says that the amount of computing performance doubles approximately every 18 months. And actually, if you look at the chips, we're actually doing a little bit better than that. But in the case of deep learning, we actually do way better than that, if my slide will show. Let's see, there's that. Okay, I'm not sure what happened there. So CPUs on an exponential scale are following Moore's Law, but we have things like GPUs that have written libraries that can do the computations in parallel. And whereas a CPU like from Intel or AMD might have, say, 4 to 8 cores, these will have hundreds to thousands of cores. And so you can get typically 2 orders of magnitude improvement of computation speed by using GPUs. And some places now are starting to build FPGAs or field programmable gate arrays that do some of the computations even faster than GPUs. And then beyond that, there are things called qubits that do quantum calculations, and who knows how much faster that might be. But the point is that we're doing way better than Moore's Law because of some of this parallel computation. Another point that I hear often is that you need millions of exams to train and use deep learning methods. Essentially, it says that if you have so much compute power, you will learn each example image unless you get into having millions of them. But I think quite honestly, that's just not true. There are a number of techniques that you can apply to get around the challenge of the need for millions of images. In general, these techniques are referred to as data augmentation, and it's essentially you create variants of the data that are different enough that they help learning, but they're similar enough that the key teaching point is kept. So some examples of this is that if left and right side don't matter, you might mirror it left and right. So usually, for instance, the brain, the left and right halves look pretty similar. A brain tumor is going to look the same. You might flip it top bottom, and again, for some structures that doesn't matter. You might rotate it 1 degree, 2 degree, 3 degree, 4 degree, 5 degrees, and on up. And you know, a human is going to have no problem recognizing a finding if it's rotated a few degrees. But to a computer, it's going to look different, and so it will learn the general concept of what a tumor looks like rather than the specific example. Ditto with, you can play with the contrast a little bit, something where a human will look past it and the computer algorithm can look past it as well. You can do other things like add noise. So now we typically see where we can create tens to hundreds of thousands of times more examples, and therefore we do effectively have the millions of examples that are required to train these tools. Another way that you can avoid the need for large data sets is what's called transfer learning. This has been published quite a bit in the literature as well. And essentially what you do is that you train the system on some type of problem that's similar, for which you do have millions of examples. And similar actually can be fairly broadly termed, in that, for instance, some of the applications in medicine actually started with the networks that were trained on photographs, like from ImageNet, and they took those neural networks and they froze most of these layers. In other words, we're not changing the weights and connections between them, and instead we just change the weights at the very end. And again, it seems like we would be learning about colors and shapes of dogs and all that, but it turns out this actually works reasonably well. So you can train it on photographs of everyday things, and then you can train it specifically for medical problems and do reasonably well. So at this point, I hope you understand we're feeding in raw images, and so the one big benefit of deep learning compared to conventional machine learning is that deep learning finds features as well as the connections, as opposed to traditional machine learning that really just does the connections or weights. So whereas with traditional machine learning, we had to handcraft the features and then feed that into a classifier, the deep learning method actually learns the features and does the classification. And that's a key difference. We don't have to feed in our bias of what we expect to see. We can instead say, here's the image, here's the right answer, and the computer figures out what are the important features or aspects of an image to solve the problem. That's really exciting. So the third driver is that there's been a huge investment in artificial intelligence in healthcare. Okay, so we're used to seeing, these huge companies like GE, Siemens, and Philips. Actually, they're much larger than Epic, Cerner, and McKesson, but of course, the market cap reflects all the non-medical stuff that these companies do. But then realize the relative size of companies like Apple, Google, and Facebook. And these companies are putting in a huge amount of money into deep learning. And as you saw, an awful lot of the technology that they are developing can translate very efficiently into the medical imaging space. So really, there is a lot of investment that's going to continue to drive our understanding of deep learning and improve the capabilities. Just within healthcare, it's estimated that something like $1.5 billion has been invested in artificial intelligence in the last couple of years. So this is a key concept here, is that as we think about what the impact of machine learning and deep learning will be on us, our natural human thought process is that we always look at the rate of change today and project what that will be in the future. Even if we try to get the very narrowest trajectory at the current point, we always underestimate it because the trajectory is an exponential. And so the correct projection for further out is always a lot more than we expect. Bill Gates said that we always overestimate the change that will occur in the next 2 years and underestimate what will occur in the next 10. And I think given the rapid pace of change in theoretical understanding of deep networks, the rapid advancement of computing technology, and the substantial investment, I think we are going to way underestimate what deep learning can do in medicine and in medical imaging. So that, I think, gives us two choices. I've gotten a lot of feedback through social and otherwise saying, Erickson, what are you doing? You're destroying our careers. But quite frankly, this is going to happen whether or not we try to do the research we do or not. And so really we have two choices of either engaging them or ignoring them. And this is the choice of the person who says, I'm going to ignore it, I'm going to keep reading x-rays like I always did. And it will happen to us. It just means we want to have a choice about how it works in. And what I find really exciting is that I think there's an awful lot of information in images that we simply don't see and probably will never see as humans. So here's one example of some recent work out of my lab where we look at MGMT methylation of brain tumors. So this is something that there's no paper that shows that radiologists can reliably figure out MGMT methylation status. But here we tried both conventional neural networks and now this new residual neural networks, and we're better than 90% accurate at figuring out MGMT methylation status on brain tumors. And actually, for those of you who do neurosciences work, you know that's actually close to what pathology is. Pathology is not 100%, both because of testing errors, but also because sometimes they can't get adequate tissue to perform the test. We have similar results for 1p19q. I thought I had that slide in there. 1p19q also fails. Another non-tumor task is that we want to figure out properties of kidneys. So this is actually some research work we do in polycystic kidney disease. And today we have technologists who trace the volume of the kidneys, and this is comparing two different tracers of the kidneys, and you can see they have pretty good agreement. But then we applied a deep learning method, and you can see now our algorithm is as good as human, and you know, I don't see very many scientific applications where you get an R-squared value like that. So we can now very precisely identify the contours of polycystic kidneys, and if you do much abdominal imaging, you know sometimes some of those kidneys can look really bizarre, and you can get disease in the liver, making this a really challenging thing. But now if you've identified what is kidney tissue, you can also start to access some of this invisible information. So we looked at whether or not we can predict who will be in end-stage renal disease based on a baseline MRI, and then looking at their clinical status 8 years later. Now, the standard was to look at the height-adjusted total kidney volume as well as the baseline eGFR. And that would predict at something like a 0.67 area under the curve. Textures were at about 0.85, and if you combine them, we're at nearly 0.9 accuracy for predicting who will be in end-stage renal disease based on an MRI acquired 8 years earlier. I think this is the yet another example of how there is so much information in the images. I'm not worried about computers replacing me. I'm excited for all the information and how much improved patient care we will get when we apply these algorithms. So really it's a question of replacement versus complementing. I think the algorithms for machine learning are really rapidly improving. The hardware is really rapidly improving, and the amount of change in, say, 20 years is almost unimaginable. And it's important that we be prepared and that we be flexible about our career. For those of you who remember back to the advent of Lotus 123, which is kind of the predecessor of Microsoft Excel, the prediction when this came out is that all the accountants would be put out of a job within 5 years. In fact, the number of accountants who exist today is greater than it was back then. And in fact, what it has done is that the accountants are no longer running adding machines, they're actually adding value by having you think about what is in the images. So I'm just about to wrap up here. I think that deep learning is going to produce reasonable preliminary reports for high volume exams, and I think that that structure will enable the systems to learn a lot more. And I think it will also promote quantitative imaging like what I showed you with the kidneys. And so for me, I actually view them as tools that we have to engage in, and that will actually make radiology a lot more interesting. Let's see. So I want you to remember 3, 2, 1. What are the three things? Theoretical advances, huge leaps in computing power, boatloads of money. We have two options, whether to engage or let others do it to us. And the one most important thing is that we have to take care of the patient. So with that, I'll say thank you and hand it back over. Now, I will stop webcasting, and I think that will give control back to you, Eric.
Can you hear me? Can you hear me? Can you hear me? Okay, yes. So, Bradley, thank you very much for this excellent lecture. And I would now like to invite the audience to send us some questions or to ask some questions in the chat box. Maybe this is possible. I hope you understood me. Okay, Brad, maybe you can tell me a bit more about how you are getting information to um, set up these algorithms and to do this scientific research. Where do you get your information and how do you gather those data?
Uh, for the data that we work from, we actually mine our image archive and our medical records, and that's actually a fairly laborious task. We have to go through, and particularly if we're looking to find things that are not in the radiology report, like the MGMT status, the 1P19Q status, whether they're in end-stage renal disease, we have to go through the medical record. So that's actually quite a bit of effort, and again, kind of reflects my goal is not so much to replace the radiologists and just say, well, what was the report? Okay, I can figure that out. I really think there's a lot of information there that can really improve the care of patients that we want to go after. So that's really the approach. And then the algorithms, we all write our code from scratch. So we currently use a library called Keras, which then sits on top of TensorFlow. The reason we do that is that it gives us a lot more flexibility, and while people do get reasonable results with transfer learning from systems that started for photographs, I do think that some information is lost there, and that may be why some of the results we get with the radiogenomics of predicting that might be that we're seeing that they find things that are not visible, but photographs are built for what the human visual system wants to see. So that's our approach. I do also see a question in the question box saying medical legally is deep learning in the end just like CAD on steroids? And I think the answer is yes. CAD can employ any number of image processing methods, and in a sense, a trained deep neural network is just another image processing tool. So I do view it as being very much like that. And I will.
Okay, thank you. I'm looking at the chat box. I don't see any other questions. So maybe another question. When do you think the first applications will be clinically usable?
So,
Can you hear me now?
yes, there are actually, I'm aware of 2 FDA cleared applications in the US. I don't follow the European market as closely, but there's one from a company called Arterys and another one from a company called Enlytic. And I had a debate with a friend of mine, Elliot Siegel, at a meeting, and in the end he said there's just no way that the FDA is going to clear this stuff. And at the time that did seem like a big hurdle, but if there were FDA people in the audience, they had to be laughing to themselves because within a couple months, the FDA clearance was published, so they had to know that it was well along. So at least in the U.S. anyway, there are 2 products I'm aware of that use deep learning technology.
Okay, thank you. Do you see any other questions in the chat box?
I don't see any other questions. I see there's a separate question tab, and there's something written in Russian that I don't understand.
On the upper line, you mean?
Yeah. Uh,
No, I don't understand it either. But okay, I think maybe when, as far as I can see, the most participants are thanking you for this good lecture. Um, so apparently there's nobody else who is having some interesting question at this moment. So maybe then we can finish the webinar here. And I would also like to inform the audience that the webinar will be available on the Zomi website for viewing afterwards. So Brad, I thank you again, and I hope to stay in touch and see you in the near future. Thank you.